Welcome to class. In the last video, we saw how to use the method of undetermined coefficients to solve non-homogeneous linear higher order equations. And if you haven't seen that video, I'd recommend you check it out because some of the core logical arguments there are going to show up again in this video. But what we saw with that method is that it can require a lot of intuition, guesswork, and trial and error. So is there a more surefire way to do it? Sure is. Turns out the way we can do that more straightforwardly is a way we've already seen to solve these equations before. Recall way back when we talked about a first-order linear non-homogeneous equation, like this guy, written in standard form, dy dx plus p of xy equals q of x. The way that we found our particular solution in that case was we assumed it was the same as the complementary solution, though we didn't have those languages at the time. But rather than it just being some constant or some parameter times the complementary solution, we allowed that parameter to vary. And that's why we called this method variation of parameters. Based on that variation of parameters, we were able to find the general solution. And then we kind of swept it under the rug. And we just turned to integrating factors for these guys instead. Now, in this section, we're going to reopen that can of worms a little bit and dive into the deep end, well, a little more confidently. Let's just move to second order for now to see what happens. What happens if I have a second order equation instead of a first order? Well, turns out it doesn't matter the order. I can still write them in standard form. It's just rather than making sure the first derivative has a coefficient of 1, I make sure the highest derivative has a coefficient of 1. So I've got this d squared y dx squared plus some function of x dy dx plus some function of xy equals some function of x. And previously we assumed that the particular solution would just look like some constant multiple of the particular solution, or some multiple I should say, not constant multiple. We're going to do the same thing here. We assume that the particular solution is going to be a linear combination of the fundamental solutions, or in other words, some constant multiple of the complementary solution. Right? It's going to look like the complementary solution, except that I shouldn't have constants or parameters in my particular solution. I should just have a function of x. So what we do is we allow our parameters to vary. And rather than writing them as constants, I'm going to write them as functions of x. Mu1 of x, y1, plus mu2 of x, y2. And now I'm going to solve this in the same fashion as my method of undetermined coefficients, except it's going to be a little bit more theoretical or general. So I just cleaned up a bit, condensed our thoughts. We are trying to find the particular solution of this second order linear non-homogeneous equation given our fundamental solutions, y1 and y2. Remember, there's two of them because it's second order. And what we're supposing is that our particular solution looks just like our fundamental solution, except that, or excuse me, just like our complementary solution, except that the parameters are allowed to vary. Mu1 and mu2 are functions of x, not constants. And I'm going to follow in the same footsteps as my method of undetermined coefficients by plugging this into the left-hand side, and I should be getting the right-hand side. I'm going to use that information to help us build the general solution here. To do that, I'm going to need the derivatives. Yp prime, I need to use the product rule. I get mu1 prime y1 plus mu1 y1 prime plus another product rule, mu2 prime y2 plus mu2 y2 prime. Going into the second derivative, I need to use 4 product rules. But I will simplify and condense this down here. I get mu1 double prime y1 plus 2 mu1 prime y1 prime plus mu1 y1 double prime. And then I get the same thing with 2's. Plus mu2 double prime y2 plus 2 mu2 prime y2 prime plus mu2 y2 double prime. Next, I'm going to plug this into the left-hand side of our equation. And I'm going to simplify that down a bit, and I'll come back with the cleaner version. And here it is. There is a lot of algebra to get down to this point, combining like terms and factoring things out and all that good stuff. So if you feel up to the task, it's a good exercise to try and come up with this form on your own. But if you're like me and a little too lazy to do that, most of the time, take it on faith from me for now. So here's what I get when I clean up the left-hand side of my differential equation. And there's a couple of key ideas I want to point out here. First of all, everything in this parenthesis is 0. How do I know? y1, if you recall, is a fundamental solution to the differential equation, which is a solution to the homogeneous or the complementary equation. In other words, if I were to replace r with 0, y1 is a solution to that. Well, that's exactly what I have here. Right? This is all equal to 0. And wouldn't you know it, it's the same thing with the next term too, except just with y2's. y2 is also a fundamental solution, which means for our non-homogeneous problem, it makes the left-hand side 0. That term is all 0. And these two pieces at the bottom are the only ones that remain. So what I now have is I have all of this stuff should equal r of x. Let's get some of this clutter out of the way. All right. So here, I cleaned up one more time, and where we left off is based on this trial function, we know that the left-hand side should equal this guy, but if this trial function is a solution to the equation, it should equal r of x. Now, last but not least, I'm going to use one last clever trick to simplify the left-hand side. And it requires a bit of intuition, so if you need to pause the video after I write it down to go back and verify it for yourself, I'd encourage you to do that. But do you notice the derivative of this guy is almost this guy? Let's look at just mu1 prime y1. When I take its derivative by the product rule, I get mu1 double prime y1 plus mu1 prime y1 prime. Now that does leave me with an extra mu1 prime y1 prime over here, right? But the full derivative of this guy is contained over here. So I'm going to simplify it, the left-hand side, by writing that this is the derivative with respect to x of mu1 prime y1 plus mu2 prime y2. And what do I have left over? Well, I've still got that p of x times mu1 prime y1 plus mu2 prime y2. And then I also have an extra mu1 prime y1 prime plus mu2 prime y2 prime. And that should all equal r of x. So what I get now is that the derivative of mu1 prime y1 plus mu2 prime y2 plus p of x times the same thing plus mu1 prime y1 prime plus mu2 prime y2 prime equals r of x. I'd encourage you to pause the video here to verify that, or I guess convince yourself that this is the same as the line above. I would also encourage you to buckle up because I am going to now impose a condition that may feel a little bit like cheating, but hear me out. I'm going to choose that mu1 prime y1 plus mu2 prime y2 has to equal 0. And I hope you see why that's an attractive choice, because then both of these terms go away. But the ability to do that might be in question here. So I want to help convince you that this is a totally valid, logical move to make. When I initially set up my trial function, I said it depended on two separate functions of x. But the choosing two different ones was a totally arbitrary choice, and it actually allotted me a degree of freedom. It's the fancy name for it. But essentially, do you notice under this condition, I could write, for example, that, and I'm going to put this in a little thought bubble here, that mu2 prime is just equal to negative y1 over y2 mu1 prime. So really, at the end of the day, I only have to make one choice. I just have to choose mu1 prime. Oh, and sorry, I guess I'll extend my thought bubble here. So really, I just need to choose mu1 prime. And then my trial function is actually just the integral of, or I suppose I should say mu1 y1 plus the integral of negative y1 over y2, which are both pieces of information that I know, times mu1 prime y2. That's just an ugly thing to write down. It's much nicer to write this down, right? But at the end of the day, really, this is kind of the argument that I want to make, that my particular solution depends on y1 and y2 in this way. It's just easier to read if I call them two separate things. But calling them two separate things lets me impose one condition on how those two are related. And this is my choice. If you don't believe me that that's valid, come say it to my face. Otherwise, okay, here is my choice. Okay? Now, based on that choice, accept it. Accept it for now. You're going to have to. You're going to have to learn to move on. Both of these terms disappear now that I've got zeros, and it just leaves me with mu1 prime y1 prime plus mu2 prime y2 prime equals r of x. Remember, y1 and y2 are things that I know. Those are fundamental solutions to the homogeneous equation. Mu1 and mu1 and mu2 are my unknowns. And in a weird way, I've written them as mu1 prime and mu2 prime, but tomato, tomato, right? Mu1 prime and mu2 prime are my unknowns. I know everything else in this system of two equations. And in fact, that system is linear in mu1 prime and mu2 prime. This is a lot of clutter, though. So once again, I'm going to clean up and see in a second. Once again, I have cleaned up our work a little bit and put a pin in where we last left off. So here is the trial function that we have selected. We have arrived at this linear system of equations to find mu1 prime and mu2 prime. And I can solve this system of equations in one fell swoop using a trick from linear algebra called Cramer's rule. Cramer's rule says that both of my unknowns will have the determinant of the matrix on the left-hand side in the denominator. Same goes for mu2. And in the numerator, they will have almost the same thing, except in the unknowns corresponding column. So for first unknown, first column, second unknown, second column, I will replace the column in the matrix with the right-hand side. So over here, I replace column 1 with 0r. Over here, I replace column 2 with 0r. And to clean this up a bit, that numerator on the left and the right, I'm going to call w's. So here's w1, here's w2. And wouldn't you know it, the denominator is the Wronskian, hence the w's. Remember, y1 and y2 are fundamental solutions. So we know that they are linearly independent. So we know their Wronskians are non-zero. So we know that these two things exist. Mu1 prime is w1 over w. Mu2 prime is w2 over w. And remember, at the end of the day, after I take these determinants, those are just some functions of x. I am just one integral away from finally having my particular solution. Let's clean it up one more time. Well, the thing to clean up is the final result. Now we have everything that we need to write down the general solution to the second order linear non-homogeneous equation, written this way. The general solution, of course, is still the complementary solution plus the particular solution. The C1 and C2, those come from my complementary solution, but we see that both pieces depend on the fundamental solutions to this equation, y1 and y2, and the particular solution has a variable parameter, mu1 and mu2. Mu1 is found by integrating w1 over w being the Wronskian of all of my fundamental solutions, w1 being the Wronskian if you replace the first column with zeros, except in the last slot you put in r. Same thing, just replace it with 2. In fact, if you want to go to higher order, nth order say, you do that for each fundamental solution. For each fundamental solution, you take the Wronskian of all of them, you compute wi by replacing the ith column with a bunch of zeros until you get to the last spot where you put r. And I'd love to show you an example of that, but this video is already far too long, and I'm sure you're not at all mentally exhausted from watching it, so I think I'll just save it for the next one. See you then.